to put some numbers on some of the concepts that we talked about, and in particular how to quantify aesthetic preferences and these kind of things. So thank you very much for joining us.
Thank you. Good afternoon, everyone. My name is Ortensia Forni. I'm a future PhD student at the chair of Econophysics in Paris, and I'm glad to be here today to talk about color distribution in nature, a data-driven exploration of color harmony and aesthetic preferences. I carried out this research in the last months during my internship under the supervision of Alexandre Darmon and Michael Benzaken. The starting point of our research have been the work of a previous PhD student, Sami Lakal, about beauty and structural complexity in black and white images. He shows that given this set of grayscale images for different level of entropic complexity, we can see in this plot where on the vertical axis we have the scores, and so the level of appreciation, and on the x-axis alpha, so the level of entropic complexity, we can see how the maximum level of appreciation is reached for a specific level of alpha close to 1. That is an intermediate level of alpha, but I don't want to go into the details because Alexandre will tell you more about this topic during his talk on Saturday at 11. But what's interesting to notice is that the level of alpha of entropic complexity close to 1 that maximizes our level of appreciation is the same that we can find in patterns in natural images. And so these results suggest the potential existence of universal criteria for aesthetic judgment. And as a continuation of this work, on my side, I will focus on colors. So before starting, we need a preliminary step about colors and how to work with colors. There are so many color spaces, and I will show you just a few examples. We can start from one of the oldest, that is the Munsell color space, and it is defined by 3 variables. Value standing for lightness on the vertical axis, then chroma standing for saturation along the radius, and hue on the angles. This color space is discrete, and it was based on human perception, and that's why for each hue we have a different number of possible value of saturation that each hue can assume. And another example is the RGB color space that is more common, and it is best used for screen viewing, and it is defined by the 3 variables red, green, and blue. Or we have the HLS color space defined by hue, lightness, and saturation. It is similar to the Munsell color space because they share the same variables, but it is continuous and it is more precise because for each hue we have the same interval of saturation value that each hue can assume on the interval 0, 1. Or a last example can be the syllab color space. So from all of them we can see that working with colors means working in a 3-dimensional space. And so we need to handle at the same time 3 parameters. The motivation of our work has been a long-standing question about color and about color harmony, and in particular, how can we combine color to produce a pleasant effect? During the history, lots of theory have been proposed, and this is just an example. This is the Moon and Spencer color theory proposed in 1944, and it was defined in the Munsell color space. And if we do an horizontal section of this 3-dimensional structure with an horizontal plane, we obtain a circle that is this circle that is the so-called U-wheel. And this theory states that if we fix a color at 0, this color is supposed to go well with all the other colors falling in the white regions, while it is not supposed to produce a pleasant effect with colors falling in these gray sectors. But unfortunately, we have no information about how this theory has been built. And so the problem of this theory and of most of other color harmony theory proposed in the last years is that they lack in quantitative large-scale approach. And so there is, even if they are still used nowadays as reference in different fields, there is no general consensus among them. And so that's why it's worthwhile to conduct a truly quantitative study on the appreciation of color combination, adopting a truly quantitative approach. And that's why we built our own experiment, and we work in the HLS color space, and we focus on the hue only, keeping the other 2 parameters fixed in order to reduce the dimensionality of the problem. We extracted 18 colors equally spaced on the hue wheel, and then in order to make them more easily distinguishable, we remove 5 of them, and we end up with the 13 different colors, and we combine them together in this way. We structure the question combining each color with the remaining ones. So here we have an example of one question showing color palette, sharing as reference color red combined with all the others. Or this is another example with light blue as reference color. And each question asks to choose the 3 most and the 3 least harmonious color combination. And each participant answered to 6 questions randomly chosen among the 13. From this survey, we collected more than 350 answers from people living mostly in France and in Japan, but in general spread across all Europe. And this is how we structure the data that we collected. We can focus on this light blue that corresponds to 200 degrees, and we can use it as a toy example for the moment. And in this plot, we have on the x-axis all the colors that we can combine with this light blue. And the green bars correspond to the frequencies of each color combination ij, chosen as one of the 3 best. And the same we can say about the red bars that correspond to the normalized frequencies of each color combination ij, chosen as one of the 3 worst. And these frequencies are normalized by the number of people that answer to that questions. So this was just an example about light blue, but we can collect all the data in a single matrix where the entry of each entry of the matrix is this Fij, defined by the difference between the best frequencies and the worst frequencies. And so each entry of the matrix represents an overall score assigned to each color combination ij. And we can see how this matrix shows a quasi-symmetric structure, meaning that there are no biases in how we structure the survey, and there are no biases based on the local arrangement of colors in the color palette that we used. And if we focus on the line, we can see how by construction they are normalized, and so each entry, all the entries of each line sum to 1, and each line corresponds to a question. But if we look at the columns, looking at the columns allows us to filter the data based on the secondary color and not on the reference color. And if we look at this column corresponding to this light blue that we used before, we can see how the columns is all green. And this is a signal that in the columns carry a bias based on the absolute preferences of colors. And is on that signal that we would like to focus now. So we would like to answer to the question about how likely is a color to produce harmonious combination with the others. And to measure this quantity, we introduce a matrix called combinability index that is the sum over the columns. And we can see in this plot the results. And it's clear how these colors, so light blue and this cluster of blues, and also yellow and orange, are the colors that are more likely to produce harmonious combination when combined to all the other colors, while red, green, and purple are the less likely to produce pleasant effect when combined with other colors. But now, if we compare these results about combinability to the results about absolute preferences of colors, so how much we like a color taken independently, and these results are taken from a previous study about color preferences, we can see how the 2 curves behaves quite similarly, meaning that the colors that we like in an absolute manner are the same that tend to form a more harmonious pair. But now, as the next step, if we would like to focus on the relative position of hues in a color palette instead of focusing on a specific hues, we have to redefine the frequencies that I introduced before. So before we had Fij, where I was the reference color, so this light blue, and J were all the other possible colors that can be combined to I. Now we have to define rotated frequencies, so Frik, where I is still the same reference color, but K is defined as the angular distance of J from I. And so intuitively, we can think about the U wheel. We can rotate it such that the reference color I is set at 0, and then we can define K as the angular distance of J from I. In doing so, and averaging over I for each K, we can obtain some region of universal appreciation and universal dislike based on the angular distance with respect to the reference color. And in this plot, we can see how there is a strong signal in this region that seems to be appreciated from everybody's perspective. So if we fix a color at 0, this color produce a pleasant color palette with colors falling in these regions with these angular distances. And we cannot do the same with the colors at close to 60 degrees or 300 degrees. And so it follows that colors that are close to each other don't produce a harmonious color combination. But now if we come back to our starting point, where the level of entropic complexity that maximizes our level of appreciation was the same that we find in natural images, we ask ourselves if there is a correlation between human preferences and natural occurrences. And to do so, we selected a dataset of 4,000 images representing different natural landscape. And for each image, we extracted the predominant color, and we studied the occurrences we studied the angular distances of all the other hues in each image with respect to the reference color. And we obtained this gray histogram about the color distribution in nature. And it's clear how, from this peak, it's clear how also nature is made of contrast colors. And overlapping the two, and so looking at these plots together, it's clear that we can, in nature, we can find a signal about our preferences. And our human preferences align with what nature offers. But if we plot these regions of universal appreciation and dislike on the U wheel, using the standard deviation as an error bar, we can see that there is a high value of standard deviation, but the variability of these results is due to the difference of each hue, of each color, and so because they behave differently. And if we look at this example and we consider red and purple, we can see how they behave in a different way. Because if we fix red at 0, and if we look at the colors falling in these regions at an angular distance of 40 and 60 degrees, we can see how the color combinations are really appreciated. But if we fix purple at 0, colors at 40 and 60 degrees combined with purple are really disliked. And a possible explanation of this behavior can be found in the plot of the combinability index. And so the color harmony theory of Moon and Spencer that I introduced before, that was proposed as a universal theory, doesn't seem to be so universal. And it's clear that universality in color harmony theory is not so obvious. And so now we extracted these regions of universal appreciation and dislike, and we ask if from the original matrix collecting all the raw data, we can extract which color contribute the most to that signal. And as I said before, this matrix has a quasi-symmetric structure, and it is confirmed by the proximity of its eigenvalues to the real axis. And so in order to simplify the interpretation, we symmetrize the matrix, and we focus on a symmetric version of this matrix. And these are the eigenvalues of the symmetrized matrix. And we focus on the first highest, on the first 6 highest eigenvalues in absolute value. And from each of them, we reconstructed the original matrix using at each time each eigenvalue and the corresponding eigenvector. And if we focus on the first reconstruction, that is the one that accounts for the most variance, and so it is the one that contains more information, and if we apply a simple shift in the lines and in the columns, such that color starts from orange and not from red, we obtain this reconstructed matrix, and it's clear how colors can be split in two groups, in two clusters, one going from orange to light blue, and the other one from this light blue to red through purple. And it's clear how colors belonging to the same group go well with colors belonging to the second group and don't go well together. And the same for the second group with respect to the first one. And this information and so we can say that within group combination are less harmonious, while cross-group ones are more appreciated. And this perfectly aligns with the signal that we extracted before, explaining why the contrast regions is so appreciated, because it's made up of combination of colors belonging to different groups. While this region of dislikes come from the fact that we are combining colors that are close to each other, so they belong to the same group. And so to conclude from the data that we collected from our survey, we can say that preferred colors tend to form more harmonious pairs. And then even in the context of color harmony, human preferences seem to align with what nature offers. And finally, it doesn't seem to exist a universality in color harmony theory due to a strong hue dependence. And the next step is to take also lightness and saturation into account in order to work with more than one parameters. And I thank you for your attention, and if you have questions, I would be happy to answer now or during the poster session tomorrow.
Thank you. Yeah, very nice. Very good reference also to the poster session. But we'll have time for some questions now. I thought there was, yes.
Thank you. That was super interesting. I just wondered about cultural differences between color preferences, because you said that in your study you mostly had people questioned from Europe and Japan. Yeah. So could you see any differences between the two groups? Because intuitively it would feel like colors are so encoded with our cultural backgrounds, with ideas about colors symbolizing certain things in a given society, that there might be some differences. And I was just wondering whether that's something you were interested in or that you tried to think of in your research. Thank you.
We split the data based on where the participants come from, and we saw that we have that the data are consistent for the green regions. So for the appreciated regions, it seems to be consistent across different countries and so different culture. And we have some small differences in the regions of dislike. But we have more answers from France than from Japan, and so the result is not so strong, but that's what we can see from the data.
Hi, thank you for your talk. It was very interesting. I wanted to go back to the slide when you extracted the colors from the natural scenes. So you are basically using them as a baseline, right? To compare if human perception is of colors is in line with what nature offers or something like that? I mean, because you mentioned you extracted the first prominent color. Yes. And also the second, I guess, to see whether they were...
No, we extracted the predominant color, and then we study the position of all the other hues in the same image, but with respect to the reference, to the predominant color that we extracted and that we set as the reference color. Okay. In order to have this plot with the 0 that is the reference color for all the images.
Okay, thank you, that was my question.
Wonderful. Maybe one last question. I don't know.
Thanks for the talk. Also on this, how did you pick the images? Because if it's from the internet, they're pretty images, right? And so you're saying it, you know, we're aligned with what's in nature, but actually maybe it's just a kind of a bias to, you know, what we actually put on the internet.
Yeah, we selected a data set of 4,000 images, and we chose it such that it was not biased based on a specific region in the world, but it contains most different landscape as possible in order to mix them all together and have a more universal result. So combining forests, mountains, lakes, and coming from all over the world.
Okay, thanks.
One last question.
Thanks. I was just curious if you have any understanding or guess about the relation between these two groups and where they're placed on the spectrum of the visible light. Because it seems to me that the top group is like the middle and the bottom group is like the extrema, or?
Yes, the order of colors in this color bar are the same that we have in the U wheel. Starting with orange instead of red, but the order is the same.
Okay, wonderful. short question with a short answer. I love that. Thank you very much again to Ortensia.